In this video, we will discuss applications of the first derivative. A function f is increasing on an interval ab if for every two numbers x1 and x2 in ab, if f of x1 is less than f of x2 whenever x1 is less than x2. A function f is decreasing on an interval ab if for every two numbers x1 and x2 in ab, f of x1 is greater than f of x2 whenever x1 is less than x2. We say that f is increasing at a number c if there exists an interval ab containing c such that f is increasing on ab. Similarly, we say f is decreasing at a number c if there exists an interval ab containing c such that f is decreasing on ab. The rate of change of a function x equals c is given by the derivative of the function at that number. As a result, the derivative is a good tool for determining the intervals where a differentiable function is increasing or decreasing. This leads to an important theorem. If f prime of x is greater than 0 for every value of x in an interval ab, then f is increasing on ab. If f prime of x is less than 0 for every value of x in an interval ab, then f is decreasing on ab. And if f prime of x equals 0 for every value of x in an interval ab, then f is constant on ab. Find the interval where the function f of x equals x squared is increasing and the interval where it is decreasing. The derivative of f of x is x squared equals x squared is f prime of x equals 2x. Since f prime of x equals 2x is greater than 0 if x is greater than 0, and f prime of x equals 2x is less than 0 if x is less than 0, f is increasing on the interval from 0 to positive infinity and decreasing on the interval from negative infinity to 0. Remember that the graph of a continuous function cannot have any breaks. As a consequence, a continuous function cannot change sign unless it equals 0 for some value of x. This leads to the following procedure for determining the intervals where a function is increasing or decreasing. Find all values of x for which f prime of x equals 0 or f prime is discontinuous, and identify the open intervals determined by these numbers. Then select a test number c in each interval found in step 1 and determine the sign of f prime of c in that interval. If f prime of c is greater than 0, f is increasing on that interval. If f prime of c is less than 0, f is decreasing on that interval. Determine the intervals where the function f of x equals x cubed minus 3x squared minus 24x plus 32 is increasing and where it is decreasing. The derivative of f of x is f prime of x equals 3x squared minus 6x minus 24, which is equal to 3 times x squared minus 2x minus 8, which is 3 times x minus 4 times x plus 2. So f prime of x equals 0 when x equals negative 2 and when x equals 4. It is a polynomial function, so it is continuous everywhere. This results in 3 intervals we must consider to determine where the function is increasing or decreasing. From negative infinity to negative 2, from negative 2 to 4, and from 4 to infinity. We choose one value from each interval to test, negative 3, 0, and 5. When x equals negative 3, f prime of x equals f prime of negative 3. I put the negative in the wrong place, it appears, which is 3 times negative 3 squared minus 6 times negative 3 minus 24, which is 27 plus 18 minus 24, which is 21. And that's greater than 0. The function is increasing from negative infinity to negative 2. When x equals 0, f prime of x equals f prime of 0, which is 3 times 0 squared minus 6 times 0 minus 24, which is negative 24, which is less than 0. The function is decreasing on the interval from negative 2 to 4. When x equals 5, f prime of x equals f prime of 5, which is 3 times 5 squared minus 6 times 5 minus 24, which is 75 minus 30 minus 24, which is 21, which is greater than 0. The function is increasing on the interval from 4 to infinity. Find the intervals where the function f of x equals x to the 2/3 is increasing and the intervals where it is decreasing. The derivative of f of x is f prime of x, which is 2 over 3 times x to the 1/3 power. It is never equal to 0, but it is discontinuous when x equals 0 and nowhere else. So there are two intervals to consider, -infinity to 0 and 0 to +infinity. We choose one value from each interval to test, -1 and 1. When x equals -1, f prime of x equals f prime of -1, which is 2 over 3 times -1 to the 1/3, which is -2/3, which is less than 0. The function is decreasing on the interval from -infinity to 0. When x equals 1, f prime of x equals f prime of 1, which is 2 over 3 times x times 1 to the 1/3, or 2/3, which is greater than 0. The function is increasing on the interval from 0 to infinity. The extrema of a function are the places where the graph of the function reaches a high point or a low point and are also called maxima and minima. A function f has a relative maximum at x equals c if there exists an open interval ab containing c such that f of x is less than or equal to f of c for all x in ab. A function f has a relative minima at x equals c if there exists an open interval ab containing c such that f of x is greater than or equal to f of c for all x in ab. A critical number of a function f is any number x in the domain of f such that f prime of x equals 0 or f prime of x does not exist. Points on the graph of the function that occur when x is a critical number are called critical points. Relative extrema of a function can occur only at critical points, but not every critical point is a relative extreme. To find the relative extrema of a continuous function f, first determine the critical numbers of f, then determine the sign of f prime of x to the left and right of each critical number. If f prime of x changes sign from positive to negative as we move across a critical number c, then f has a relative maximum at x equals c. If f prime of x changes sign from negative to positive as we move across a critical number c, then f has a relative minimum at x equals c. And if f prime of x does not change sign as we move across a critical number c, then f does not have a relative extremum at x equals c. Find the relative maxima and relative minima of the function f of x equals x squared. The derivative of f of x equals x squared is f prime of x equals 2x. If f prime of x equals 0, then x equals 0, which is the only critical number of f. F prime of -1 is 2 times -1, which is -2, which is less than 0. And f prime of 1 is 2 times 1, which is 2, which is greater than 0. Since f prime is negative when x is less than 0 and positive when x is greater than 0, we can conclude that f of 0 equals 0 is a relative minimum of f. Find the relative maxima and relative minima of the function f of x equals x to the 2/3. As we saw in a previous example, the derivative of f of x equals x to the 2/3 is f prime of x equals 2/3 x to the -1/3. F prime is not defined at 0 and is continuous everywhere else, but never equal to 0. X equals 0 is the only critical number of f of x. In that previous example, we also saw that f prime of -1 is -2/3 and f prime of 1 is 2/3. Since f prime is that keeps happening, I'm sorry. Since f prime is negative when x is less than 0 and positive when x is greater than 0, we can conclude that f of 0 equals 0 is a relative minimum of f. Find the relative minima and maxima of f of x equals x to the 4th minus 3x squared minus 24x plus 32. The derivative of f is f prime of x equals 3 times x plus 2 times x minus 4, as seen in a previous example, and it has zeros at x equals -2 and x equals 4. Since the derivative is a polynomial, it is continuous everywhere, and -2 and 4 are the only critical numbers. We also saw that the function is increasing on -infinity to -2, decreasing on -2 to 4, and increasing on 4 to infinity. From this information, we can conclude that x equals -2 is a relative maximum, and x equals 4 is a relative minimum.